All right, welcome to Calculus. We're going to look at a power series here, and we're going to see what we can do with it. And the big question that we're going to ask is, does it or does it not converge? That's the question we want to be concerned with, is does it converge? And that's the question we ask most of the time, and every time we're dealing with a series, is because if it converges, it means that there's a sum that sum is equal to. That summation, that whole thing is equal to a particular number. If it doesn't converge, it means that sum just keeps getting bigger and bigger and bigger, and we can't figure out what that value is, that exact value is. And it's very useful for us to understand that we can figure out what that value is. So if we're talking about e to some power, well, that has a series that converges, which means that we can find the sum, which again is useful to us. That's one of the reasons why we care about it. All right. So, but the one we're going to look at here is n equal to 1 is our starting place going off to infinity. And we're doing x minus 3 raised to the n power over n. And we're wondering, does this series converge? Okay. And if it does converge, it actually falls into three possibilities. It converges everywhere. It only converges under a particular guideline, meaning it's inside of realm of numbers or possibilities, or it only converges when x is equal to 3, where we're centered at. Those are the three possibilities that we're dealing with. But this should be centered. This should converge at least somewhere. If nowhere else other than just when x equals 3. And you say, well, how do we? Why does that have to be one of those scenarios? Can't this be divergent at some point? Not this one, because we have x minus 3 as the numerator, right? And all the values for n here are positive, which means that x minus 3 is always going to be in the numerator. So when x is equal to 3, we'll just do that one real quick. When x equals 3, you have 3 minus 3 raised to the n power over n. So that is 0 raised to the n power over n, which is just simply 0. So you're adding all the zeros together, which is simply equal to 0. So it always converges there. That would be what we call a trivial case. But does it converge everywhere else? So let's look at that. How do we deal with this? Now, when I look at these things, remember we can first identify what about the nth term, okay? Well, the thing that's easier, a little bit more difficult here, is the fact that we have this x value, which is unknown, and n, which is our variable for the summation. So we really kind of need to play around with this a little bit. And this is where having our series test is useful to us. And my go-to one is always the ratio test. If I can't use the ratio test, then I do other things. But that's useful to us here because the ratio test simply means that we want the limit as n goes to infinity of the next term over the current term. The current term, you can think of that being that expression that we have right there inside the summation. The next term would be just plus 1 of that. So x minus 3 raised to the n plus 1 power over n plus 1. All that is over x minus 3 raised to the n raised to the n power over n, right? Now, we do a little bit of calculations here, and keep in mind that it's kind of understood that these are the absolute value of these pieces, right? So we're going to do the limit as n goes to infinity, and we're putting this in absolute value for a reason. And if you look back at the rules for the ratio test, the thing that we want that limit to be equal to a particular number, right? And that kind of forces us into this wanting this or needing this to be an absolute value here as we deal with this. So anyway, we go through this process here, and we're going to have strike that. We're going to have x minus 3 to the n times x minus 3. I'm just splitting up that power there. All that's over n plus 1. And then I'm going to have that times the reciprocal of the denominator there. So that's over n over x, x minus 3 raised to the n power. And those two pieces are going to, of course, cancel, still inside the absolute value bars there, right? So now we got the limit as n goes to infinity of some stuff we can simplify here, right? So we have n over n plus 1 times the absolute value of x minus 3. Now let me just kind of address this. I can move all the n stuff outside of the absolute value sign because n is already positive. All right, n was the value or the counting value we're using for the summation, and that by its sheer nature has to be at least non-negative. And in this particular instance, if you look back at the original summation I started with, it was n equal to 1. So the n values start at 1 and they get bigger, so they're never negative. So we're doing a positive divided by a positive, so that's always going to be a positive number. Now the question then becomes is what do we do with this at this point? How can we rearrange this? What do we deal with this? So if you just plug infinity into here, you get infinity over infinity, which is not something we can process very easily. But since that is an indeterminate case, we can use L'Hopital's rule, which means we have 1 over 1, right? So now you're doing the limit as n goes off to infinity of 1 over 1 and then times x minus 3, right? L'Hopital's rule does meaning if you have one of the indeterminate cases, the two that are interesting to us are infinity over infinity and 0 over 0. So I can do 1 over 1 just by doing the derivative of the top, derivative of the bottom. I'm not doing quotient rule. I'm doing the derivative of the numerator. I'm doing the derivative of the denominator. In both cases, it gives me 1, which means I'm just doing the limit of 1. So now the limit as n goes to infinity of the absolute value of x minus 3 is equal to x minus 3. And you're still inside the absolute value. Now, the thing about the ratio test was we wanted this to be less than or equal to 1, right? So we wanted x minus 3 to be less than, or actually just less than 1. If it was equal to 1, it was actually inconclusive. We didn't know what it told us. When it's greater than 1, it's going to diverge. When it's less than 1, it's going to converge. So all I need to do is force this or assume this to be less than 1, right? And that means that x minus 3 has to be less than 1, not less than or equal to, just less than 1, and simultaneously greater than negative 1, right? So we need it to be in that realm, that we need to be in that range of values there. So if I add 3 in all 3 spots, I end up with 2 is less than x, which is less than 4. So what we found here is that when this x value is between 2 and 4, this series converges. So the summation when n equals 1 to infinity of x minus 3 raised to the n power over n converges when x is less than 4 and simultaneously greater than 2. And if you remember, 3 was that trivial case. 3 is in that realm. But what we also found is this also works when it's 3.9 or 2.1 or 2.001. We found an entire range of values here that do actually work. And another thing we might want to look at is, well, can we plug in 4? The ratio test that we could, we wanted it to be strict inequalities, but let's go back and plug in 4. What happens to the original thing there if we plug in 4? We get 4 minus 3, which is 1. 1 raised to the n power is always 1, so you have 1 over n. Well, if you're talking about the summation of 1 over n, that's a p-series with a p-value of 1, which that diverges, right? So it can't be 4. X can't be 4. But what about if it's 2? In that case, you'd have 2 minus 3 over raised to the n power over n, right? In that case, you end up with negative 1 raised to the n power over n, which actually converges, right? And if you're not familiar why that converges, this is what we call an alternating series, okay? It's an alternating series. And the definition or the idea behind an alternating series is that it will converge as long as it passes the nth term test, right? Another name for this might be a harmonic series from time to time. You might see it that way. But this is an alternating series, which means that each term is going to change sign, which means it's actually going to get smaller faster than just something without any negative signs in there. Each time you subtract off and add and subtract off and add. And each time you subtract and add, you're adding a little less and you're subtracting a little less. So that sum is actually converging to a particular value because of the alternating properties of this thing. So what we're going to do here is we're actually going to add an equal bar right there, right? So the reason we added that equal bar was because this is an alternating series. And because it's an alternating series, the 2 needs to be included in the convergence interval. What we actually call this is our convergence interval. If I can write. Okay, and here we also have a radius, right? We have a radius of convergence. In this case, the radius of convergence is half the width of the interval, which is in this case just 1, right? And we're centered at x equal to 3. So it's a radius of 1 was centered at 3, which can be very useful to us when we start digging in on other problems. But we can also just simply say that the convergence interval is between 2 and 4, 2 included in the interval. All right, I hope this was useful. If you need additional support or questions, please ask. I'll be more than happy to post as I can. Also, you might need to go back and review alternating series. What I suggest you do is you find a sheet. You can find them all over the place of all the different series, the different convergence tests rather of the series, and normally they have it lined up so that you have the condition and the setup that you need to go through and do, and it's just kind of this little stereo instructions, if you will, on how to do those different tests. And that can kind of walk you through that process. So notice that we did actually pay attention to a couple different things. We did the ratio test, and after we're done with the ratio test, we actually went back and said, well, what about the P series? What about the alternating series? Because those became possibilities when we did this. All right, take care and keep mathing on.